Welcome to Q-square approach. In this video, we'll solve the linear programming problem by using graphical method, which gives an unbounded solution. If you have watched the previous video, then it will be easy to understand this problem. The link for the previous video is given in the description. Before we solve this problem, we'll see what is unbounded. When the value of the decision variable may be increased indefinitely without violating any of the constraints, the solution space or feasible region is called unbounded, and the value of the objective function may increase indefinitely in this region for maximization. The problem is maximize z is equal to 6x1 plus x2 subject to the constraints 2x1 plus x2 greater than or equal to 3 and x2 minus x1 greater than or equal to 0, x1 comma x2 greater than or equal to 0. We will take all the constraints as equation. From the first constraint, we have 2x1 plus x2 which is equal to 3. If x1 is equal to 0 in this equation, it implies x2 is equal to 3. The points are 0, 3. Suppose x2 is equal to 0 in the same equation, then we have 2x1 which is equal to 3, which implies x1 is equal to 3 by 2 which is equal to 1.5. So the point is 1.5, 0. From the second constraint, x2 minus x1 which is equal to 0. From this, x2 is equal to x1. If we give x1 is equal to 0, then we have x2 is also 0. So the point is 0, 0. If we give x1 is equal to 1, then we have x2 is also 1. So the point is 1, 1. Actually, these 2 points 0, 0 and 1, 1 will form a straight line which passes through the origin. Now we'll draw the graph. We'll take this as x1 axis, this one as x2 axis, this is the origin. The points are 1, 2, 3, 4, here 1, 2, 3, 4. Now the points are 0, 3 and 1.5, 0. 0, 3 is here, 0, 3 and 1.5 is here, 1.5, 0. Now we are going to join these 2 points by the straight line. The name of this equation is 2x1 plus x2 greater than or equal to 3. Now we draw the second line, you see, which is passes through the origin. The name of the line is x2 minus x1 greater than or equal to 0. Now we'll set the region for the line 2x1 plus x2 greater than or equal to 3. Since we have greater than or equal to sign, we have to set the region opposite direction. That is, we have to set the region in the opposite direction to the origin from the line. So this is the line. So opposite direction, origin is here, so opposite direction is here. Okay. Since we have greater than or equal to sign in the constraint. So this is the saddle region for the first constraint 2x1 plus x2 greater than or equal to 3. The second constraint is very tricky because this line split the first quadrant equally at 45 degree. So we have to set the region for this line carefully. The constraint is x2 minus x1 greater than or equal to 0. So x2 greater than or equal to x1. Now we'll take any point satisfying this constraint. So 2 greater than or equal to 1, that is x1 is equal to 1, x2 is equal to 2. The point 1 comma 2 satisfies this constraint x2 greater than or equal to x1, and also this point 1 comma 2 lies in the region, actually lies here, there is 1 comma 2 is here. So we set this region Now we have to identify the common region for these two constraints. If you observe this graph, then this is the common region for these two constraints, and if you note this common region carefully, so this not bounded by any line, this region is going indefinitely, it's going like that, it's increasing indefinitely. This common saddle region, that is this feasible region, solution space is unbounded. Now the vertices of this unbounded region are, this will take as A and this B. B is 0,3, but we don't know the point A. So for that we can solve this two line x2 minus x1 is equal to 0 and 2x1 plus x2 which is equal to 3. If we solve these two equations, we will get the point A. So minus 3x1 which is equal to minus 3, so x1 is equal to 1, then x2 minus 1 which is equal to 0, so x2 is also 1, so A is 1 comma 1, so the vertex A is 1 comma 1. Actually this A and B are the only known vertices in the unbounded region. The vertices of the unbounded regions are A is 1 comma 1 and B is 0 comma 3. and the objective function is maximize z is equal to 6x1 plus x2. Now we are substituting this point x1 is equal to 1 and x2 is equal to 1 in the objective function. Then we have maximize z is equal to 6 into 1 plus 1, which is equal to 7. If we substitute this point x1 is equal to 0 and x2 equal to 3 in the objective function, then we have maximize z is equal to 6 into 0 plus 3, which is equal to 3. Suppose the region is bounded, then this 7 will be the optimum solution for this problem. But we have an unbounded region, so the value of the objective function is more than 7. Therefore, the problem has an unbounded solution. The given problem has an unbounded solution. Note: suppose the objective function for this problem is minimize z is equal to 6x1 plus x2, and the rest of the things are same. That is, the vertices are a is 1, 1, b is 0, 3. So these are the vertices. So minimize z is equal to 6 into 1 plus 1, which is equal to 7 at the point 1, 1, and then at the point 0, 3 minimize z is equal to 0 plus 3, which is equal to 3. So this is this 3 is the optimum solution for the objective function minimize z is equal to 6x1 plus x2. Even we have an unbounded region, so the optimum solution is minimize z is equal to 3 at the point 0, 3 even we have an unbounded region. So this 3 is the optimum solution when the objective function is minimize z. Thank you for watching.